There is a single layer of mud pulled up from the floor of the Pacific Ocean off Northern California that is stacked in the wrong order. In a normal earthquake deposit, the heavy sand settles on the bottom and the fine silt drifts down on top. This core is upside down. Fine silt on the bottom, coarse sand above it. And the only clean explanation scientists have found for that flipped layer is that two enormous earthquakes struck the same stretch of coast within minutes to hours of each other, while the dust of the first one was still falling through the water. That layer sits at the exact place where the two most dangerous fault systems in the western United States almost touch. To the north, the Cascadia Subduction Zone, the fault that runs roughly 1,000 kilometers from northern California up past Vancouver Island. The fault scientists call the source of the big one. To the south, the San Andreas, the fault that destroyed San Francisco in 1906. For most of the last century, emergency planners treated these two as separate problems with separate timelines. A new study out of Oregon State University, built on more than 130 ocean floor cores and revived in the news this spring, argues that on at least a handful of occasions they were not separate at all. They went off together. The last time this happened, in the winter of 1700, a magnitude 9 earthquake sank the Pacific Northwest coast and threw a tsunami across the entire Pacific to Japan. The sediment record suggests the northern San Andreas may have ripped in the same window. Today, the population living on top of that combined hazard runs into the tens of millions, and the official death toll for just the Cascadia half of it, in Oregon and Washington alone, has been estimated by FEMA at around 14,000 people. So here is the question this video is built around. Not how big the big one will be. We have argued about that for decades. The question is whether the big one comes alone, or whether the moment Cascadia lets go, it reaches down the coast and pulls the trigger on a second giant before anyone has even climbed out of the rubble of the first. If you find this kind of breakdown useful, subscribe and tell me in the comments which coast you are watching from, because the people in the corridor are exactly who this is for. Now let me show you where that upside down layer came from, and why one scientist almost threw it away. Part 1. The layer that should not exist start with the thing that does not fit, because in this story everything flows from it. When the seafloor shakes hard enough, the loose sediment piled on the edge of the continental shelf gives way. It slides downhill in an underwater avalanche, a fast, dense river of mud and sand called a turbidity current. When that current finally slows and stops, it drops its load in a very particular order. The heavy grains, the sand, fall out first and land on the bottom. The light grains, the silt and clay, stay suspended longer and drift down last, settling on top. Geologists have a name for the deposit this leaves behind. They call it a turbidite. And a turbidite almost always reads the same way from bottom to top, coarse then fine, heavy then light. It is one of the most reliable patterns in marine geology. The core that started this whole investigation does the opposite. Fine on the bottom, coarse on top. Light, then heavy. It is, in the simplest terms, an earthquake deposit assembled backwards. There are only a few ways nature can do that, and most of them do not survive scrutiny. A single landslide does not sort itself in reverse. A storm strong enough to move that much coarse material would leave other fingerprints that are not there. The explanation the researchers kept circling back to is almost unsettling in how simple it is. The fine bottom layer settled out from one earthquake. Then, before that settling could finish, a second large earthquake hit and sent a fresh, coarser avalanche down on top of the still falling cloud. 2 quakes. 1 sediment package. stacked in an order that only makes sense if they happened very close together in time. The reason that matters has nothing to do with mud and everything to do with maps. The place this core came from sits near the Mendocino Triple Junction off Northern California, the seam where the southern end of the Cascadia Subduction Zone runs into the northern end of the San Andreas. It is one of the few spots on Earth where two great fault systems sit close enough to leave their signatures in the same pile of sediment. So a backwards stacked deposit at that exact location is not just a curiosity. It is a possible recording of the northern Cascadia Fault and the northern San Andreas firing in sequence, captured the only way an event from before written records could be captured, in the layers of the seabed. The lead scientist on this work, marine geologist Chris Goldfinger of Oregon State University, has spent decades reading these layers. His reaction to the implication is worth sitting with, because it reframes the entire conversation the West Coast has been having about its future. We are used to hearing about Cascadia as the worst case, the single catastrophic event the region dreads. Goldfinger's blunt summary of what the doublets suggest is that the lone Cascadia rupture may not be the worst case at all. There may be a worse one above it, and we have been measuring the wrong thing. That is the central rule break of this entire story. The mental model almost every plan is built on is that the big one is one event, in one region, at one time. The upside down layer says that model has, at least a few times in the geologic past, simply been wrong. And the rest of this video is the chain of evidence that connects that one strange core to a scenario that no emergency plan in the country is currently designed to survive. To trust that chain, though, you have to know how the core was even found, because it was not found on purpose. It was found by mistake, in the middle of the night, by a research ship that was in the wrong place. Part 2. The wrong turn off Cape Mendocino the Discovery starts with a navigational error in 1999. A team was out on a research cruise to do exactly what Goldfinger had built a career on, drill into the seabed off the Pacific Northwest to read the history of Cascadia earthquakes. The plan was to core the Cascadia margin, the offshore stretch where the great subduction quakes leave their turbidite record. But a wrong latitude was entered, the kind of small data entry slip that sends a ship steadily off its intended track through the night. By the time the error was caught, the vessel was roughly 90 kilometers, about 55 miles, south of where it was supposed to be, south of Cape Mendocino, out of the Cascadia Zone entirely, and into San Andreas territory. Goldfinger has described waking up to find the ship well off course and being, in his own words, pretty unhappy about it. But they were already there, sitting over a submarine canyon near Fort Bragg called Noyo Canyon. And rather than burn the time steaming back, he made the call that ends up being the hinge of this entire study. They dropped a core right where they were. This is worth pausing on, because the trustworthiness of a scientific claim often comes down to how the data was gathered. This was not a core collected to prove a theory about linked faults. Nobody set out that day looking for a connection between Cascadia and the San Andreas. The location was an accident. That actually strengthens the finding rather than weakening it, because there was no expectation shaping where they drilled. They pulled up a record of roughly 3,000 years of seafloor history from a spot they had not meant to visit, and that record contained the repeating, backwards stacked pattern that did not match anything in the textbook. From there the work became deliberate and slow, which is the part that separates a real study from a headline. One strange core proves nothing. So over the years that followed, the team gathered and examined more than 130 sediment cores up and down the coast, north and south of that triple junction, building a library that spans something on the order of 3,000 to 30 100 years of geologic time. They were not chasing a single sensational layer. They were testing whether the pattern repeated, whether it showed up in the right places, and whether the timing held together when you dated it independently. That is the difference between a curiosity and a case. A curiosity is one anomaly you can explain away. A case is the same anomaly showing up again and again in the right geographic position, surviving every attempt to give it a more boring explanation. The Noyo core was the curiosity. The 100+ cores were the attempt to turn it into a case, and to turn sand into a timeline, they needed a clock. The clock they used is one of the most reliable tools in earth science, and it is the reason this study can make claims about events that happened centuries before anyone on this coast was writing anything down. That clock is built into the shells buried in the mud, and it is how a layer of sediment becomes a date. That is where we go next, because once you understand how they read time out of the seabed, the pattern they found stops sounding like a guess and starts sounding like a record. Part 3. Reading AN earthquake in the mud, the honest question any skeptic should ask is simple. How can anyone claim 2 earthquakes happen minutes to hours apart, 300 or 1,000 or 1,500 years ago, from a tube of mud? It sounds like the kind of overconfident leap that gives this whole genre a bad name. So let me walk through exactly how it is done, because the method is more careful than the headlines make it sound. There are 2 clocks at work, a coarse one and a fine one, and they answer 2 different questions. The coarse clock is radiocarbon dating. Buried in those sediment layers are the shells of tiny marine organisms. While they were alive, they took in carbon from the ocean, including a trace amount of a radioactive form of carbon that decays at a known steady rate. The moment they die, that intake stops and the clock starts. By measuring how much of that radioactive carbon is left in the shells just below a turbidite, scientists can estimate how long ago that layer was laid down. This is what lets them say a particular earthquake deposit dates to roughly such and such a century. It is not perfect. It carries a margin of error that can run to decades. But across the whole West Coast record, it lets the team line up a Cascadia layer in one core with a candidate San Andreas layer in another, and ask whether they fall in the same window. That coarse clock is how you get the long pattern, the claim that over the past 3,000 years there were at least 8 large San Andreas earthquakes that landed within a few decades of a major Cascadia quake. Within decades is a loose word. It is suggestive, not proof of a same-day event. It tells you the 2 faults seem to cluster in time more than chance would predict, but on its own it cannot tell you whether a given pair went off in the same hour or 20 years apart. That is where the fine clock comes in, and the fine clock is the upside-down layer itself. Radiocarbon cannot resolve minutes, but the physics of falling sediment can. When that first earthquake's avalanche settles, the fine silt at the top of the cloud takes a known, limited amount of time to drift down and come to rest. If a second avalanche of coarse sand lands on top of that silt before it has fully settled, you get the backwards order. And the only way that happens is if the second quake struck inside that narrow settling window. Not decades later, not even days later, in most readings. Minutes to hours. The reversed grain order is, in effect, a stopwatch frozen in the rock, so the team's strongest claim is built from 2 layers of evidence working together. The radiocarbon clock says these faults cluster across the centuries. The flipped doublet layers say that on at least a few of those occasions, the second rupture came almost immediately. When you put those together, you get the headline finding, stated carefully in 3 separate cases within roughly the past 1,500 years, the cause are best explained by Cascadia and the northern San Andreas rupturing within minutes to hours of each other. 3 confirmed near-instant doublets, a wider pattern of clustering behind them. It is worth being clear about what this is not. It is not a direct observation. Nobody watched these quakes happen. It is an inference, and the scientists who made it say so plainly. The doublet structure is the best available explanation for a feature that is genuinely hard to explain any other way, and that is a real and meaningful thing in geology, but it is not the same as a seismograph trace. We will come back to exactly how strong that inference is, and where other scientists push on it, because honesty about the soft spots is what makes the rest of this credible. But before we get to the doubts, we need to meet the one event in this record that is not soft at all. The one we can date almost to the day. The one the title of this video is pointing at. Because the most recent time the upside down layer appears to have formed, the second quake in the stack, the people on the far side of the Pacific wrote it down without ever knowing what it was. Part 4, January 26, 1700. For most of Cascadia's history, we are reading shells and silt. For one night we have a date. On the evening of January 26, 1700, at around 9 o'clock Pacific time, roughly 1,000 kilometers of the Cascadia megathrust let go in a single rupture. The best estimates put it between magnitude 8.7 and 9.2. which is to say right around a magnitude 9. The seafloor lurched. The coast of what is now Northern California, Oregon, Washington, and British Columbia dropped by 1 to 2 meters in moments, and the shaking is thought to have lasted on the order of several minutes, a duration almost impossible to imagine if your only reference is a few seconds of rattling. There were no written records on this coast at the time. The way we know the date so precisely is one of the great detective stories in earth science. About 10 hours after that rupture, a tsunami arrived on the Pacific coast of Japan. It came with no warning and no felt earthquake, because the earthquake that caused it was an entire ocean away. Japanese officials in villages along the Honshu coast recorded a strange destructive wave, somewhere in the range of 1 to 5 meters, washing in on a calm day. For 3 centuries those records sat as a minor mystery. They called it an orphan tsunami, a wave with no parent. The parent was found by working backwards. Scientists could date the death of whole forests of red cedar and Sitka spruce along the Pacific Northwest coast, trees whose roots were suddenly dropped into salt water and killed when the land subsided. Those ghost forests still stand in places today, grey trunks rooted in tidal mud. Tree ring dating placed their death in the winter of 1699 to 1700. Native oral histories along the coast, from Vancouver Island down into Northern California, carried accounts of a night the ground shook and the sea came in. And the Japanese tsunami records, cross-checked against wave travel time models, pointed back across the Pacific to a source on the Cascadia margin at about 9 that night. 4 completely independent lines of evidence, from drowned trees to foreign village ledgers to oral tradition, converging on a single date. That convergence is why 1700 is one of the most confidently dated prehistoric earthquakes on the planet. Now connect it back to the mud. In the doublet record off Cape Mendocino, the most recent of those backward stacked layers appears to line up with this 1700 event. The reading the study supports is that the Cascadia rupture is the lower, finer layer, and the northern San Andreas is the coarse sand stacked on top, the second shock that struck while the first one's debris was still in the water. If that reading is right, then the last great Cascadia earthquake was not a solo event. It was the opening half of a doublet, and a second giant followed it almost immediately along the northern San Andreas. This is exactly what the title is reaching for, and it deserves a careful phrasing rather than a dramatic one. The claim is not that we have a Japanese ledger describing the San Andreas half. We do not. The 1700 Cascadia quake is rock solid. The idea that the northern San Andreas joined it is an inference from the sediment, strong enough to take seriously, not strong enough to call settled. So the responsible version of the title's promise is this. The last time a megathrust of this size struck this coast, the geologic record suggests something more may have followed it within hours, and that possibility is the entire reason this new study matters. Hold on to that distinction between what is dated and what is inferred, because it is the spine of the honesty in this story. Next, we slow down and translate the technical vocabulary that gets thrown around in coverage like this, because words like megathrust and magnitude and subduction zone are doing enormous work, and most of them are quietly understating what they describe. Part 5. What the words actually mean if the language sounds routine. The danger hides. So let me make a few of these terms concrete, because each one is carrying more weight than it sounds like. Start with subduction zone. The Cascadia Subduction Zone is the boundary where one slab of the Earth's crust, the Juan de Fuca plate, is being forced down underneath the North American plate. The two are not sliding smoothly. They are locked together, snagged, and the continent is being slowly bent and compressed as the pressure builds, sometimes for centuries. A subduction zone earthquake is what happens when that snag finally releases all at once and the overriding plate snaps upward and seaward. That upward snap of the seafloor is what launches a tsunami. This is the same machinery that produced the 2011 Tohoku disaster in Japan and the 2004 Indian Ocean catastrophe. Cascadia is the same type of fault, the kind that produces the largest earthquakes the planet is capable of. Now megathrust. It is not a marketing word. It is the technical term for that locked low-angle subduction boundary, and it is reserved for the faults that generate magnitude 9 class events. When you hear megathrust, you should hear the upper end of what is physically possible. Magnitude is the term most people misread. The scale is not linear, it is logarithmic, and that detail is the whole game. Each whole step up the magnitude scale represents about 30, 2 times more energy released. So a magnitude 9 is not a little stronger than the magnitude 7 quakes that already make news. It releases on the order of 1,000 times more energy. Comparisons to the 1906 San Francisco earthquake, itself a catastrophe, put a full Cascadia rupture at something like 40, sometimes more powerful. The number creeps up by 2 digits. The reality multiplies by a factor most people never intuitively grasp. Then there is the distinction the new study leans on hardest full margin versus partial rupture. Cascadia does not always break along its entire length. Sometimes only the southern portion ruptures, producing a smaller, though still major, quake. Sometimes the whole 1,000-kilometer fault goes at once, which is the magnitude 9 full margin scenario. This matters for the doublet idea because it is the southern full margin reach of Cascadia, the part nearest the Mendocino triple junction. That sits close enough to load stress onto the northern San Andreas. Geometry is destiny here. The two faults can talk to each other precisely because of where they nearly meet. And finally, the word at the centre of the evidence, turbidite, which we have already met. It is just the fingerprint an underwater avalanche leaves in the seabed, normally coarse on bottom and fine on top, and it is the only witness we have for earthquakes that predate the written record on this coast. Notice what all of this adds up to. None of these terms is exaggerated. If anything, the plain bureaucratic sound of them, subduction, magnitude, margin, hides the scale of what they describe. A magnitude 9 megathrust on a full margin rupture is among the most violent events the Earth produces, and the official vocabulary describes it in the flattest possible voice. That gap between how mild the words sound and how extreme the reality is exactly the trap this kind of hazard sets. People hear familiar terms and round the danger down. Now that the words are real, we can get to the part the study actually contributes that is new. Not that Cascadia is dangerous, we knew that. The new piece is the mechanism. How could one of these faults reach across to the other and set it off? That is not obvious, and it is where the science gets genuinely interesting and genuinely uncertain. Part 6. How one fault pulls the trigger on another. The idea that two separate faults could go off almost together sounds, at first, like coincidence dressed up as a theory. So the real test of this study is whether there is a physical mechanism that makes it plausible. There is, and it has a name. The researchers describe it as a form of partial synchronization. Here is the core of it. When a great Cascadia earthquake ruptures, the energy it releases does not simply radiate out and fade. The rupture physically moves enormous blocks of the Earth's crust, and that movement changes the stress on every nearby fault. A fault is not an isolated thing. It is part of a connected system, and when one piece shifts, the forces on its neighbours shift too. The technical concept is stress transfer. A big rupture can load extra stress onto an adjacent fault, nudging it closer to its own breaking point. The geometry here is what makes Cascadia and the San Andreas special neighbours. They very nearly meet at the Mendocino triple junction off northern California. So when the southern end of Cascadia ruptures in a full margin event, the sudden shift in the crust delivers a jolt of stress right onto the northern tip of the San Andreas. And this is the crucial part. That jolt does not have to be enough to break a relaxed fault. It only has to be the final push on a fault that was already loaded, already near failure on its own. If the northern San Andreas has spent decades or centuries quietly building toward its own rupture, the arrival of Cascadia's stress can act as the trigger, the last straw that tips an already strained system over the edge. The first quake does not create the second one's energy. The second fault supplies its own. The first quake just decides the timing. That distinction is the whole reason this is frightening in a precise rather than a vague way. We are not talking about one earthquake somehow becoming twice as big. We are talking about two independent disasters, each carrying its own stored energy, being released in the same narrow window because one set off the other. Two full reservoirs, one breaking the dam for the other. It also explains a detail in the data that would otherwise be strange. The synchronization in the record appears to run mostly one direction, north to south. Cascadia appears to trigger the San Andreas, and the reverse is much harder to find. That fits the mechanism. A massive full-margin subduction rupture delivers a far bigger stress change to its neighbour than the narrower San Andreas can send back the other way. The direction of the trigger follows the size of the push. But I want to be careful here, because this is where the honest line sits. The mechanism is plausible. It is grounded in stress transfer physics that scientists use routinely on smaller faults, and the marine geologist quoted in independent coverage notes the general idea of nearby faults synchronizing has been seen at smaller fault boundaries before. What it is not is directly observed at this scale. The exact way stress travels between two such different fault systems, one a subduction megathrust, the other a strike-slip fault, is still worked out mostly in computer models rather than watched in real time. The mechanism makes the doublet possible. It does not make it certain on any given Cascadia rupture. So the picture so far is a strange core, a careful method, one solidly dated event, real vocabulary, and a believable mechanism. The next question is whether the pattern is rare enough to dismiss or common enough to plan around. And the count the team came up with is the part that should make any West Coast emergency planner put down their coffee. Part 7. 8 times in 3,000 years, a single doublet could be a fluke. A pattern is a different thing entirely, and the numbers are where this stops being a curiosity. Across the roughly 3,000 years of record the team assembled, they identified at least 8 large San Andreas earthquakes that occurred within decades of a major Cascadia quake. 8 times, in other words, the two faults appear to have gone off close together in geologic terms, far more often than you would expect if they were truly independent systems rolling their own separate dice. Independent faults should not keep landing in the same window. These two do. Inside that broader clustering sit the sharper cases. In 3 instances within roughly the past 1,500 years, the cores show the full upside-down doublet signature, the one that points not to within decades but to within minutes to hours. Those are the events where the second rupture appears to have followed almost on the heels of the first. And the most recent of those 3 is the one that lines up with 1700, the event we can date almost to the day. Let me put the rhythm in plain terms, with the appropriate caution about dating margins. Beyond 1700, the record points to closely timed pairs in earlier centuries, including a cluster in the window around the 1400s and others stretching back well before the Common Era. These are not precise anniversaries. Radiocarbon dating works in ranges, and reasonable scientists can argue about which layer pairs with which. But the overall shape is hard to wave away. Over and over, when Cascadia appears in the record, a San Andreas event appears near it. Set that against the backdrop of how often Cascadia itself fires. Goldfinger's own long turbidite record counts dozens of Cascadia earthquakes over the last 10,000 years, somewhere around 40 when you include the partial ruptures of the southern margin, and roughly 19 to 20 that appear to have torn the full length of the fault. On average, a full margin magnitude 9 comes along every several hundred years, with the gaps ranging from as short as a couple of centuries to as long as 1,000 years. We are now more than 320 years past 1700. We are not overdue in any sense that lets anyone predict a date, but we are squarely inside the window where these things have happened before. Here is why the clustering count changes the stakes rather than just adding trivia. If a synchronized doublet were a one-in-a-blue-moon freak, you could reasonably leave it out of your planning. You plan for the likely, not the freak. But a feature that shows up repeatedly across 3,000 years, with 3 near-instant cases in the last 1,500, is not a freak. It is a recognized behavior of the system, and almost none of the emergency planning for the West Coast is currently built around it. The plans assume a Cascadia event or a San Andreas event. The record keeps suggesting Cascadia and San Andreas. That gap between what the rock remembers and what the plans assume is the real subject of the back half of this story. But a careful person should be suspicious of any pattern that fits its conclusion this neatly, and there is one enormous exception sitting right in the middle of the record. One famous, well-documented San Andreas earthquake that did not follow a Cascadia quake at all. It is the most studied earthquake in American history, and at first glance it seems to break the whole pattern. Understanding why it is the exception and not the rule is where we pick up next. Part 8. The one time it went alone, the pattern's best test is the case that breaks it, and there is one that seems to do exactly that. On the morning of April 18th, 1906, the northern San Andreas ruptured for nearly 500 kilometers and tore San Francisco apart. It is the most thoroughly documented earthquake in American history. We have photographs, survivor accounts, damage surveys, and more than a century of scientific study of the surface rupture. By any measure, it was a major San Andreas event, around magnitude 7.9. And here is the problem for the synchronization story. There was no Cascadia earthquake in 1700-style proximity to it. Cascadia did not rupture in 1906. The San Andreas went entirely on its own. If the new study claimed that the San Andreas can only break when Cascadia sets it off, 1906 would demolish that claim in one stroke. So it is worth being clear about what the study actually argues, because the 1906 quake is not a contradiction. It is the control case that makes the rest of the evidence sharper. The researchers point out that the San Andreas is fully capable of rupturing alone. It is a major fault in its own right, loading its own stress on its own schedule. 1906 is the proof. What the doublet evidence suggests is narrower and stranger than full dependence. It is that, over the last roughly 2,500 years, 1906 stands out as nearly the only large northern San Andreas earthquake that was not accompanied by a Cascadia event. In other words, the unusual thing about 1906 is not that it happened. It is that it happened alone. The exception in the record is the solo rupture, not the doublet. And the sediment shows this directly, which is the part that makes it more than an argument. In the cause, the 1906 earthquake left only a thin, ordinary turbidite. A single, modest layer sorted in the normal course on bottom way. Compare that to the thick, doubled, upside-down beds left by the synchronized events, where the layer is 2 or 3 times as heavy because 2 avalanches stacked on top of each other. You can, in a very real sense, see the difference between a solo quake and a doublet with your eyes once you know what you are looking at. The thin 1906 bed is what a lone earthquake looks like. The fat inverted beds are what 2 look like. So 1906 does double duty. It proves the San Andreas does not need Cascadia, which keeps the study honest and stops it from overclaiming, and it provides the visual baseline, the thin single layer that makes the doubled layers look as anomalous as they are. Far from breaking the pattern, the most famous earthquake in the country's history is the measuring stick the pattern is read against. That reframes the 1906 disaster in an uncomfortable way. We tend to think of it as the worst-case San Andreas event, the benchmark of California catastrophe. The doublet record suggests it may have been the gentle version, a San Andreas rupture that arrived without its larger northern partner. The version that came in 1700, if the inference holds, was the one with company. There is one more thing 1906 does for us. It tells us the human stakes of even a solo northern San Andreas rupture, because we measured them. And once you know what one of these faults can do by itself, you can start to picture the corridor that a doublet would put under fire at the same time. That corridor, and the millions of people who live inside it, is where this stops being geology and starts being a map of who is at risk. Part 9. Who lives inside the corridor now put the threat on a map, because that is where abstract magnitude turns into a list of places. The Cascadia half of the hazard runs offshore from roughly Cape Mendocino in northern California, up the length of the Oregon and Washington coasts, past the Olympic Peninsula and Puget Sound, and on into British Columbia near Vancouver Island. The tsunami from a full margin rupture would reach the Oregon and Washington coast not in hours, but in something like 15 to 20 minutes, in places carrying run-up heights that official Oregon planning documents describe as reaching up to 100 feet at the most exposed shorelines. The coastal towns of Clatsop, Tillamook, Lincoln, Coos and Curry counties in Oregon, and their counterparts in Washington like Grays Harbor and Pacific County sit directly in that path. These are the communities where the warning will not be a phone alert. It will be the ground itself, shaking for several minutes, which is the signal to get to high ground on foot, because there will not be time for anything else. But the shaking does not stop at the beach. A magnitude 9 sends violent ground motion far inland. The Portland metropolitan area, Seattle, Tacoma, and the dense corridor along Interstate 5 would take severe shaking, even though they sit well back from the coast. This is where the bulk of the region's population, infrastructure, hospitals, ports, fuel pipelines, and bridges are concentrated, much of it built before modern seismic codes, and much of it resting on soft shake amplifying soils. Now overlay the San Andreas half. The northern San Andreas, the segment that ruptured in 1906 and the one the doublet evidence implicates, runs up the coast through the San Francisco Bay Area, one of the most economically critical and densely populated regions in the country. A northern San Andreas rupture is a Bay Area earthquake, so a synchronized doublet does not just mean two big quakes somewhere on the west coast. It means the Pacific Northwest coast and Puget Sound and the Portland-Seattle corridor and the San Francisco Bay Area all taking catastrophic shaking inside the same short window. I want to correct a tempting overstatement here, because getting this right matters more than making it sound bigger. You will sometimes hear a doublet described as the ground shaking continuously from Vancouver all the way to Los Angeles. That is not what the science supports. This is not one unbroken rupture running the entire west coast. It is two separate ruptures on two separate faults, close in time. The northern San Andreas does not reach Los Angeles. Its northern segment reaches from around Cape Mendocino down through the Bay Area towards central California. So the honest version is alarming enough without inflation. A doublet would put the corridor from British Columbia down through the San Francisco Bay Area under disaster conditions at nearly the same moment. That is tens of millions of people across 3 states and a Canadian province, struck not in sequence over years, but together. The population in that combined corridor is the number that should anchor everything. It is why the death toll estimates for just the Cascadia portion, around 14,000 in Oregon and Washington by FEMA's modelling, with some analyses running higher, are only part of the picture. Those numbers were calculated for the solo event. A doublet adds the Bay Area's exposure on top, in the same time frame, drawing on the same finite pool of national rescue resources. Which brings us to the dimension that the corridor map alone cannot show you. It is not only where the disaster lands, it is when and how fast and in what order the hours unfold, because the entire reason a doublet is worse than the sum of 2 separate quakes comes down to timing, and the timeline of a doublet day is its own kind of nightmare. Part 10. The shape of a doublet day. Timing is the hinge of this whole story, so walk through the clock of a doublet as the evidence describes it. It begins with the Cascadia rupture. The fault unzips along its length, and the shaking on the coast lasts not for seconds, but for something on the order of 4 to 6 minutes. Sit with that. The strongest earthquakes most people have experienced last perhaps 15 or 20 seconds. Cascadia's full margin shaking would run long enough that people have time to fall, get up, try to move, and still be standing in it. In those minutes, unreinforced buildings fail, older bridges and overpasses come down, landslides break loose across the coast range, and the soft soils of the lowland cities amplify the motion. Within 15 to 20 minutes of that, the first tsunami waves arrive on the Oregon and Washington coast. There is no meaningful gap for an official warning to be issued, processed, and acted on. The shaking is the warning. Anyone on the low coast who waits for an alert has already lost. Now insert the doublet. The stress transfer from Cascadia reaches the northern San Andreas. The new study's central, careful claim is that in the synchronized cases, the second rupture came within minutes to hours of the first. So somewhere in that window, while the Pacific Northwest is still in the opening chaos of its own catastrophe, the Bay Area's fault lets go. A second major earthquake, with its own shaking, its own collapses, and along parts of the coast its own tsunami potential. Think about what that does to every assumption built into disaster response. The standard model of catastrophe is sequential. A region is hit, and the surrounding undamaged regions converge on it with help. Search teams, medical units, fuel, water, the National Mutual Aid System all flow inward from the outside. That model has one absolute requirement. The outside has to be intact. A doublet attacks exactly that requirement. If the Pacific Northwest and the Bay Area are both broken in the same hour, then for each of them the nearest major source of aid is also a disaster zone. The regions that would normally rescue each other are both down at once. And the timing cuts another way that is easy to miss. Even the within hours version is brutal. But consider what within decades does over a human lifetime. Some of the clustered events in the record may have been separated by years, not minutes. Picture a region that has just absorbed a Cascadia catastrophe and spent a decade rebuilding, only to take a major San Andreas quake before recovery is complete. The faults do not have to fire in the same minute to overwhelm a society. They only have to fire inside the same recovery window. The minutes to hours doublet is the acute version. The within decades cluster is the chronic one. Both break the assumption that you get to recover from one disaster before facing the next. This is the genuine payoff of the new study, and it is worth stating cleanly. The contribution is not that Cascadia is dangerous, or that the San Andreas is dangerous. We have known both for a long time. The contribution is about correlation in time. It is the suggestion that these two threats are not independent draws but linked events, and that linkage is precisely the thing that defeats the way we have planned to survive them. So the next question is unavoidable. If the help is coming model assumes an intact neighbour, and a doublet removes the intact neighbour, what actually happens to the response? That is not a geology question anymore. It is a question about systems and supply lines and the brutal arithmetic of two catastrophes drawing on one set of resources. Part 11. Why help is on the way may not be true. Follow the consequence to where it actually lands, on the machinery of rescue and recovery. Modern disaster response is, at its core, a system of mutual aid. No single city or state holds enough search and rescue teams, medical capacity, fuel, heavy equipment, and emergency supplies to handle a catastrophe alone. It does not need to, because the system is built on the assumption that disasters are local and aid is national. When an earthquake hits one region, resources surge in from everywhere else. The damaged area is the patient. The rest of the country is the hospital. A synchronized doublet inverts that. Now imagine the surge that the Pacific Northwest would need after a magnitude 9, the convoys of rescuers and supplies that would normally pour up Interstate 5 from California. In a doublet, California is not the staging ground. The Bay Area is its own broken region, its ports and airports and freeways compromised, its own population trapped and waiting. The aid that Cascadia planning quietly assumes will come from the south may be sitting in the rubble of its own disaster. And the reverse is just as true for the Bay Area looking north. The bottleneck is not only people, it is the physical lifelines. The West Coast's fuel, its major ports, its long-haul transportation, its undersea and overland communication lines, and significant stretches of its power and water infrastructure all run through this same corridor. A single Cascadia event is already expected to knock essential services out for weeks, with Oregon's own emergency planners warning residents to be ready to survive without outside help for a minimum of 2 weeks, and realistically longer. That 2-week figure was calculated for the solo disaster. Stack a second major earthquake onto the same corridor, draining the same national pool of responders, damaging the same supply routes from a second direction, and the realistic self-sufficiency window does not add. It compounds. This is the concrete meaning of the phrase the study's lead author used, that the lone Cascadia rupture may not be the worst case scenario. The worst case is not simply a slightly bigger earthquake. It is 2 catastrophes engineered by their timing to neutralize the response to each other. The danger is not just in the shaking, it is in the correlation. I want to be careful not to slide from this into fatalism, because that is the failure mode of this entire subject. None of this means the West Coast is doomed or that preparation is pointless. The opposite is true. The reason this finding matters is that it is actionable. It tells planners that the assumption of an intact neighbour is fragile, which means resilience has to be built locally and in advance rather than trucked in afterward. It tells individuals that the 2-week minimum guidance is a floor, not a ceiling. The whole point of understanding the doublet is not to be more afraid. It is to stop planning for a disaster that assumes someone is coming and start planning for the hours and days when, for a while, no one can. But before anyone takes all of this as settled fact and acts on it as gospel, we have to do the thing this genre almost never does. We have to turn around and look hard at how much of this is actually proven, and how much is careful, honest inference that other good scientists are still pushing back on. Because the strength of a claim is not how scary it is how well it survives doubt. Part 12. What the scientists still cannot tell you here is where I separate what is known from what is inferred, because everything you have heard so far depends on it. Start with what is genuinely solid. The 1700 Cascadia earthquake is about as well established as a prehistoric earthquake can be, dated by 4 independent lines of evidence to January 26 of that year. The existence of turbidites and their use as earthquake proxies is mainstream geology. The general principle that nearby faults can influence each other through stress transfer is well accepted and observed at smaller scales. None of that is in question. Now the soft spots, named plainly. The first and biggest is the exact gap between the 2 quakes in a doublet. The sediment can show that a second avalanche landed on top of a still settling first one, which constrains the timing. But scientists are openly clear that they cannot pin down whether the gap was 10 minutes, 10 hours, or in some of the looser pairings, a few years. The reversed layering says soon. It does not say exactly how soon, and that range, minutes to years, is enormous in human terms. A response plan for a 10-minute gap and a response plan for a 3-year gap are completely different documents. The second soft spot is the direction of triggering. The evidence and the mechanism both suggest Cascadia triggers the San Andreas, north to south, and not reliably the other way round. But whether a San Andreas quake could ever set off Cascadia is genuinely debated, and the data leans against it more than it settles it. The third, and the one a careful viewer should weigh most heavily, is that the synchronization itself is an inference from sediment, not a direct observation, and the mechanics of how stress crosses between 2 such different fault systems are still worked out largely in computer models rather than measured in the field. The doublet beds are the best available explanation for those upside-down layers. Best available is a real and meaningful standard in science. It is not the same as proven. And there is a worthwhile counterpoint that fairness demands including. The turbidite earthquake record that this and much of Cascadia paleoseismology relies on has itself been challenged. A separate analysis raised questions about how reliably individual turbidite layers can be tied to specific earthquakes rather than to other causes like storms or local slumps. That critique does not erase the doublet finding, but it is a reminder that this is an active scientific argument, not a closed case, and that the people building this record are the first to say so. So the honest synthesis is this. The clustering of the two faults across 3,000 years is a real and striking signal. The three near-instant doublets in the last 1,500 years are a strong inference. The mechanism is plausible and physically grounded. And the precise timing, the direction in every case, and the certainty of the link are still open questions that more cause. Better dating and ongoing modelling will continue to test. Anyone who tells you a synchronised double earthquake is a certainty for the next Cascadia rupture is going past the evidence. Anyone who dismisses it as impossible is ignoring a pattern that keeps appearing in the rock. That honest middle ground is not a weakness in the story. It is the strongest version of it, and it leads directly to the only question that actually matters for the people living in the corridor. Given real but uncertain evidence of a worse than expected threat, what should anyone actually do about it? Part 13. What changes if you live here, take the uncertainty and turn it into action? Because the right response to a credible but unproven threat is not panic, and it is not dismissal. It is preparation that holds up either way. The useful thing about earthquake readiness is that almost none of it depends on knowing whether the next event is a solo quake or a doublet. The doublet finding does not change the basic actions. It raises the stakes on doing them, and it changes one key assumption about how long you are on your own. If you live in the coastal tsunami zone, from Northern California up through British Columbia, the single most important piece of knowledge is your evacuation route to high ground, on foot, without a car, because roads and bridges may be gone, and the wave arrives in 15 to 20 minutes. The trigger to move is not an official alert, it is the shaking itself. Long, strong shaking near the coast means go to high ground immediately and stay there. That instinct, drilled in advance, is what saves lives in the window too short for any warning system. For everyone in the broader shaking corridor, inland cities included, the standard guidance is unglamorous and effective. During the shaking, drop, cover and hold on. Afterward, expect that official help may be delayed, and that is the assumption the doublet finding sharpens. The long-standing regional guidance to be ready to sustain yourself for at least 2 weeks without outside services should be treated as a realistic flaw rather than a worst case, because the scenario where a neighbouring region cannot send aid is exactly the scenario this research describes. Water, medications, a way to stay warm, a plan to reconnect with family, and multiple independent ways to receive information all matter more, not less, if the help that normally arrives is delayed because the helpers are also in a disaster. Have more than one way to get alerts, because no single channel is reliable when infrastructure fails. Know where you would shelter, keep devices and backup power charged before any event, not after. Follow official evacuation orders without waiting to be convinced. And if you are in or near a coastal risk area, do not let anyone, including this video, talk you into a false sense of either safety or doom. You are not safe simply because the last big one was 3 centuries ago, and you are not doomed simply because the fault is capable of a great deal. For the institutions, the meaning is different and arguably larger. The actionable core of the study is aimed at planners. If the assumption of an intact, aid-providing neighbour is the weak link, then the work is to build resilience that does not depend on it. That means hardening local infrastructure, hospitals, fuel, water, and communications, so each region can function on its own for longer. And it means stockpiling and pre-positioning resources within the corridor rather than counting on them arriving from outside. The doublet does not demand a brand new playbook so much as it removes a comforting assumption from the existing one. The through line of all of it is the same. Preparation that assumes you may be on your own for a while is preparation that survives the discovery that your neighbour might be down too. That is the practical gift hidden inside an alarming finding. It does not ask anyone to live in fear. It asks them to be a little more self-reliant, a little earlier than the old single disaster model implied, which brings us all the way back to where we started, to one strange layer of mud stacked in the wrong order on the floor of the Pacific. Part 14, back to the upside-down layer returned to that core off Cape Mendocino, because everything we have walked through changes what it means. When we started, it was just an oddity. Fine silt on the bottom, coarse sand on top, an earthquake deposit assembled backwards, the kind of thing a scientist might have shrugged off as a quirk of one accidental drilling site. Now you can read it. That inverted layer is a stopwatch. The fine bottom is the settling cloud of one great earthquake. The coarse top is the avalanche of a second one that struck before the first had finished falling. It is, if the inference holds, the physical signature of two giants firing in the same window, written into the seabed because there was no one on this coast to write it down any other way. And the most recent time that layer appears to have formed lines up with the winter of 1700, the night the Cascadia megathrust dropped the coastline by a metre or more and sent an orphan tsunami clear across the Pacific to puzzle Japanese villagers who never felt the ground move. That is the answer to the question in the title, and it deserves to be stated with the precision the evidence allows. The last time an earthquake like this struck this coast, the geologic record suggests something more may have followed it within hours. Not certainly, not provably to the minute, but strongly enough that the scientist who has read these layers for decades now says the lone big one may not be the worst case after all. So, what has actually changed in your understanding between the first minute of this video and now? At the start, the big one was a single event. A Pacific Northwest problem, a thing the region would face while the rest of the country sent help. By the end, that picture has a crack running through it. The threat may not be one event, but two. Not one region, but a corridor stretching from British Columbia through the San Francisco Bay Area, and the very feature that makes it dangerous, the close timing, is the feature that could remove the help everyone is counting on. What remains known is the strength of 1700, and the reality of the clustering pattern across 3,000 years. What remains uncertain is the exact gap, the reliability of every individual layer, and whether the next Cascadia rupture will come alone like a quiet draw or with a partner like the doublets in the mud. What is worth watching, going forward, is the science itself. More cores, better dating, and the ongoing argument among geologists about how tightly these two faults are really bound. This is a live scientific question, not a settled prophecy, and the responsible thing is to track it as it develops, rather than to treat the scariest version as fact. And what the whole thing means, in the end, is smaller and more useful than doom. It means the comforting assumption baked into a century of planning that disaster is local and rescue is regional may not hold on the day the West Coast needs it most. It means resilience has to be built into the corridor in advance, and it means the people who live there are wise to prepare as though they may be on their own for a while. The upside-down layer is not a prediction of when. Nothing in this evidence can tell you when. It is a correction to what. The next great earthquake on this coast might not be a single catastrophe with help on the way. It might arrive with company. And now, before most people are paying attention, you understand why one backwards layer of mud changed the question the entire west coast should be asking.